morning everyone. I am in electrical engineering department and I mainly work in optical fibers, communication and signal processing areas. So, I am not with a background with this course, but regardless of whether I work in that, the basic concepts of signal processing are more or less the same across all disciplines. So, what I would like to do is to assume that you have not been previously introduced to fundamental concepts in signal processing, essentially time domain analysis and frequency domain analysis, what are the different types of signals, and then how do you analyze them in time domain, and most importantly how do you analyze them in the corresponding frequency domain, because these two domains or these two are essentially complementary to each other. For a full description of a signal, you need to know both its time domain characterization as well as the frequency domain characterization. In case you have any questions, you can feel free to interrupt me and we can discuss whatever your doubts and questions are, provided we have within the limits, time limits of this lecture. Okay, with that, let me go ahead. It is interesting that there are already pictures which are essentially going to introduce what we are going to cover, and I am sorry I do not have any slides to put up because we have a very short notice in which I had to take this lecture, but it would be interesting that most of the things that I describe here can be very easily verified for yourself by using commercial software packages or free software packages such as MATLAB and Octave. Okay. So, you can see that there are already two pictures, and presumably these pictures, one of them is the time domain picture here, because on the horizontal axis you have the time variable and on the vertical axis you have a magnitude, because probably this function f, which is a function of time, was a complex signal. So, therefore, there was a magnitude of f of t depicted out there, and there is a corresponding picture here in this so called frequency domain picture, and you can see that the horizontal axis here is a frequency variable omega. Okay. This is one domain and this is another domain, and there is a relationship between the time domain and the frequency domain, which is governed by a technique called as Fourier analysis, and we will look at some of the interesting signals and the corresponding frequency domain pictures using this Fourier analysis techniques. Okay. To begin with, let me tell you, or just reintroduce you to what is a signal. Signal is an information that normally is a function of time. In some cases, the signal could also be a function of spatial points. For example, when you click a picture or you take a video, then you, in addition to time in the video case, you also need to know the position of a particular pixel, and this would correspond to the spatial domain. So, you have mathematically a signal being represented as a function of time. It need not be just a mathematical representation, it could be a set of tables, like one column and another column the corresponding values, and you can have whatever the interpretation that you want to have. So, there is essentially the idea that there is an independent variable and then there is a corresponding dependent variable, and the dependent variable evaluated at the specific instance of at the specific instance of the independent variable. Okay. Now, when you talk about signals, you normally want to classify them into different types, so that you can understand more of the properties of these signals. For our purposes, we will assume that all the signals are going to be functions of time, but as I have told you, they need not be functions only of time, they can be functions of any other independent variable, for example, space, as I told you. Now, mathematically we represent this signal by this is the dependent variable and this is the independent variable. Different ways of representing the signals could be y of t, or you can even be more descriptive and then say something like age of t, which would represent the age of a person at a given time after that person has been born, right. So, you could have any kinds of representation, but note that in all these representations you have an independent variable which is time, and the implicit assumption in this one is that time is a continuous quantity. Okay. So, such signals in which the independent variable time is varying continuously over a range, and this range could be from minus infinity to plus infinity, are called as continuous time signals, or CTS for short. Okay. So, this continuous time signal further could be many types. Okay. The main classification of these signals further is normally done in terms of how much can we talk about the signal with great certainty and how much can we talk about a signal in terms of its uncertainty. Meaning, if the form of the function x of t is known completely in such a way that, so you have a signal which is continuous time domain or which is a continuous time signal, and then this continuous time signal is said to be deterministic signal when you can specify the properties of this x of t without any uncertainty. For example, if you had an ideal function generator which can generate different types of signals, and one of the simplest signal that it can generate is a sinusoidal signal, which we will write it as sin 2 pi f0 t, where f0 is called as the frequency of the sine wave. Okay. If you know this functional form and if the function generator is an ideal function, then no matter what time value you take, which is the independent variable, right. So, time value you take, the value of the function x of t, which is given by sin of 2 pi f0 t, is completely known. Okay. To whatever the required precision, of course, there are problems with the required precision thing, but in principle the value of x of t, there is nothing uncertain about this one. Okay. But in practice you will see that signals are not entirely deterministic. Signals can indeed be what is called as random. Okay. One simple example of a random signal is again a function generator, but that is not ideal function generator. It has a random phase phi, meaning that when you turn on the function generator, the starting point or the point where the sine function begins is little uncertain because of the fact that this phase phi is uncertain. Okay. So, you have these two major classes of functions, one is called as deterministic and the other called as random. Okay. We make this classification or we want this classification to be discussed because the tools that you use to analyze the signals which are deterministic are slightly different, in fact much different from the tools that you use to analyze random signals. Okay. Another example of a random signal could be just a noise that would come from various sources, as what you have studied in the previous lectures in this course, right. So, you have a deterministic signal and then you have a random signal. Let us first look at deterministic signals because they are kind of easier to talk about, and all the techniques of the frequency domain thing that I talked about can be introduced in a relatively simpler context with deterministic signals. Okay. So, we have discussed a major class of signals called as continuous time signals, and in that we have looked at deterministic and random signals. Then there is another class of signals which we will call as discrete time signals. Okay. And these discrete time signals are usually but not always obtained by sampling a continuous time signal. So, the connection between continuous time signal and the discrete time signal is called sampling. Okay. And I will talk a little bit about what this sampling means and how do you sample a signal, so that whatever information that is contained in the continuous time signal is faithfully reproduced in the discrete time signal as well. So, you do not want to lose information when you sample, and how do you ensure that you do not lose information in when you sample a continuous time signal is something that we are going to talk about. Okay. The difference between continuous time and discrete time signal is that in the discrete time case, this variable will usually not be a continuous range, or it will be at discrete points with respect to time. Okay. I will talk a little bit more about the notation of x of n when we talk about sampling. Okay. For now, you can take this n to be an integer, and the range of this integer could in principle go from minus infinity to plus infinity, signals that have been turned on at minus infinity and continue to go all the way up to plus infinity. But in practice, of course, you do not have that such range of minus infinity to plus infinity, you have a finite range, but nevertheless in principle x of n could range from minus infinity to plus infinity in terms of n. Okay. Now, discrete time signals also can be deterministic and random. So, the tools that you are going to use will again be different for the deterministic discrete time signals and random discrete time signals, and furthermore the tools that you use for continuous time signal deterministic will be different from discrete time signal deterministic, but there is a relationship between these two as we have seen from sampling. Okay. So, what we will do is we will postpone the discussion of discrete time signal for some time. We will first look at the tools that we use to describe continuous time signals, deterministic, then come to sampling, discrete time signals, deterministic, and then have a brief overview of random signals both for continuous time as discrete time signals. Okay. Now, if you have looked at this board, then what you would have realized is that signals can be classified into two types, discrete time and continuous time. Further, in continuous time signals you can classify them into deterministic and random signals. Okay. But beyond that, when you look at idealizations of the signal, you will also find that there are many different types of signals even in the class of deterministic itself. Okay. And those classes which will be very important for us are what are called as aperiodic signals and periodic signals. A periodic signal is one which essentially repeats after a certain time. So, for example, if we denote the periodic continuous time signal by xp of t, okay, then the defining condition for this signal to be periodic is that it must repeat after a translation of time by capital T units. Okay. Suppose I want to plot this xp of t, okay, and let us say I know how the signal looks over a range of minus t by 2 to plus t by 2. So, let us say this looks something like this. Okay. Now, how do I generate the signal values for times that is not in this range? Because I know that this is a periodic signal, what it means is that the value that you are going to get, so this is 0 and I want to generate these values for the next range, say t by 2 to 3t by 2. Please note that one range here is of a duration t seconds. This will be very critical when we go to the domain picture. So, each periodic signal has a fundamental period as we would call it, and the period of that fundamental, this one will be about t seconds. Okay. The units of time is in seconds. So, this is t seconds. To generate the signal over the range say t by 2 to 3t by 2, we now look at this expression, and what we are saying is that whatever the value of the signal at time t, right, will be the same value of the signal at time t plus nt, and n being an integer can be plus or minus. If you have a signal which is x of t, then x of t minus t will be a signal which has been delayed by a t unit, okay, and x of t plus t is a signal which has been advanced by t units. Okay. So, this delay would correspond to taking this signal as entirely as a signal and then pushing it to the right, and advancing it would mean taking this period and then putting it to the left. So, pushing it to the left. Okay. So, that is what these symbols mean. So, what when we write down x of t, which is the original signal, then to generate a translated version of x of t, you would have to push either the signal to the right, in which case you are delaying the signal, or you can advance the signal by pushing the signal to the left. So, this corresponds to changing the time origin of the signal. Okay, that is all this would mean. And to generate the signal over t by 2 to 3t by 2, you can take this signal and shift it simply because whatever the value of xp of t, for example, say at t equal to 0 will be the same value at t equal to. So, when will this be the same value? So, if you look at xp of 0, the value of that one should be the same as xp of minus t, okay. And then xp of so hold on, sorry, I got this one the other way around. Anyway, does not matter. Since I want to generate the value at say t, right, that would be equal to xp of, if I use this expression, then that would be xp of 0, right. So, forget this one and then look at the last expression. Right. So, if you look at this one, I want to generate the value of xp at the time t. Xp is the signal here which I have represented here. So, let us say this is the real signal xp of t, and the value of this xp at capital T equal to t will be obtained by this expression, right, wherein xp of, when you substitute t equal to capital T, you will see that this would be essentially xp of 0. And if I want to now obtain the value at say just about this value, which I am going to represent by this circle here. So, this star or the cross multiple would have come here, and then the circle would also be shifted by the same unit at this point, right. So, this would be the circle that has been shifted. So, if you follow this algorithm of generating any signal. So, for example, I want to generate this one at t plus some delta out there, which is just a shift after t to t plus delta, then this would be xp of delta, right. So, you can look at this way and then reproduce the signal or reconstruct the signal over the range from t by 2 to 3t by 2, and then you can keep doing this. So, now you have shifted the signal by fundamental period by 1 unit of time. You can do the same thing for another unit, and then you can keep doing it until you see that this signal will run from minus infinity to plus infinity, such that whatever the value of the signal that is there in the fundamental unit, that is sufficient for us to characterize the signal over the entire range. Is that okay? So, this is an example of a periodic signal. An aperiodic signal could look something like this. So, here it is not satisfying this relationship, because the values are not essentially repeating. The signal is essentially just one time waveform. It could be anything like this as well. So, for example, these two are aperiodic signals. There is no periodicity in them, right. Now, it is very clear if you are someone who is sitting in the audience to look at the signal there and then say, yes, that is a periodic signal, and you look at this one and then say this is an aperiodic signal, right. Why you can say that one? Because you have actually seen that this fundamental period, if I were to shade this area, you can actually see that this area has been repeated by translating the signals by capital T units, right. You can actually see this, there is no problem with that. So, it is very easy to spot a periodic signal when it has been properly plotted for you, okay. And you would say the same thing here, right. But in many cases you would not be able to plot a signal and then check and then determine that this signal is a periodic signal. If it is a periodic signal, what would be its period, and so on and so forth, okay. So, to understand those concepts wherein we cannot just by looking at the signals say that there is a periodic signal, because for example, here you can say that there could be a periodicity because there is some sort of a periodic variation, but this is also something that is getting damped out there, right. So, there is periodicity, but the function itself is getting damped, or the signal is getting damped. So, there could be periodic in some sense, but I do not know what the period is, because by looking at this it is quite hard to say what is the period and whether there is a periodicity in the underlying signal or not, right. To answer questions like that, you have to go to the complementary domain, what is called as frequency domain, okay. We have talked about time domain. This is pretty much what we can talk about in the time domain, okay. So, in the time domain you can specify the function. If you know the mathematical form of the function, that is very good, you can specify it in that way, or from some measurements, if you have constructed the function over the time period, say minus t by 2 to plus t by 2, then you can construct the function for any different value of the time, because you can simply use the periodicity property. But for this you should know that the signal is periodic, okay. So, this is one picture as we talked about time domain picture, but to answer questions like this, is there a periodic waveform in this one? If it is there, what is the period, and so on, we need to look at the so called frequency domain picture. And this frequency domain picture is called as Fourier analysis, okay. And this is something that we are going to look at first for the periodic case and then look at it for the aperiodic case. In a periodic case, you can look at the periodic case here. In the periodic case, you have a function which is repeating itself every t seconds, right. And this t seconds or 1 by t second is what is called as the fundamental period of the periodic signal. It could be of any shape, but as long as the function is repeating every t seconds, then this 1 by t will be called as the fundamental period f naught, okay. And you can also clearly see that if instead of thinking of the fundamental period as t, I could technically also think of this as fundamental period of 2t, maybe I did not go all the way out there. So, this is one picture, yeah. So, I can think of this as having a harmonic or something at sorry, not harmonic, I can think of this as a periodic signal with a period of 2t. It is possible for me to think of this as 2t, because in this one I can easily replace n by 2, and then what you will see is that the function is essentially the same. So, whether you think of this as the fundamental period t or the fundamental period 2t, when it is not really fundamental, it is just an extension of that one, you can still have that kind of a periodicity defined for this signal, and that would of course be written in terms of another period which would be 1 by 2t, but we already know that 1 by t is f naught. So, what I get is f naught by 2, right. So, I will in fact have these different frequencies coming up, and there is a general way of writing these functions, periodic functions or periodic signals, in terms of what is called as a Fourier series, okay, in which you write this xp of t as, I will first give you what is called as the trigonometric form of this series, which is given by So, this is an expression for a periodic signal with a fundamental period of t. Okay. So, the subscript p that I have used indicates that this is a fundamental period is, I mean this is a periodic signal, and capital T which you can see coming up here are the different, I mean the capital T that would essentially tell you that the fundamental period of that one is t. Okay. Look at the expression that we have written. In this there are an infinite number of terms, but there are 3 classes of terms as you can think of. The first one is a0 by 2, that is that it has no time variation whatsoever, right. So, a0 by 2 is a constant, right. How do you evaluate a0, an and bn is something that we need to look at, and I will not be able to do that one here, or I will just give you the expressions and you can do it later on for yourself. Look at the textbooks how to derive that one, but for our purposes look at this term a0 by 2 which has no time variation, then look at these terms an and bn. Okay. The terms an are getting multiplied with cos 2 pi by t times nt, and we have already defined 1 by t as f naught, right. So, I could equally have written this cos 2 pi by t nt as cos n omega naught t, where omega naught is equal to 2 pi by t, and it is called as the fundamental frequency. Okay. That is called as the fundamental frequency. N times omega naught would obviously be the integer multiple of omega naught. So, as n goes from 1 to infinity, you have different frequencies which are say omega 0, 2 omega 0, 3 omega 0 and so on and so forth. Okay. So, these are called as, after omega 0, these are called as harmonics. Okay. So, for this reason Fourier analysis is sometimes called as harmonic analysis, because you are looking for harmonics of a signal. Okay. So, this omega 0 is called as the fundamental, and the remaining ones are called as the harmonic of that fundamental. Okay. Please note that the fundamental, harmonic and so on are actually dependent on what values of the period t that you have, right. So, if the function has a different period t, then the fundamental frequency will be different and the corresponding harmonics would also be different. And you have this an which gets multiplied with cos, and then you have signals which are bn that gets multiplied with sine. If you just look at how sine and cosine waveforms look as a function of time, you will see that there is a slight difference between the way these functions are. Okay. What is the difference? The difference is that one of them is symmetric about t equal to 0. For example, if this is a cosine signal, right, this is a cosine signal. So, this signal is symmetric about t equal to 0. When we say symmetric, what we mean is that the value here is the same as the value at negative times, right. By the way, this is just an origin, this is a place of convenient choice for us, you can move it any place you want and the signal would essentially behave in the same way. So, if you choose the origin with this one, then these two values being the same causes this cosine wave to be a symmetric wave, and if you plot a sine wave, you can see that, sorry, let me plot it in a separate graph. So, if you plot a sine wave, you can see that the value here will be the same as the value here, except that the sign is different, right. So, this is called as even symmetric signal, and cosine waves are even symmetric signals when you choose the in this manner, and then this will be odd symmetric signals, because in this case the values about 0 are negative of the values about that one. So, you have an even symmetric signal in which x of minus t, which is a reflected signal, is equal to x of t, and this fellow here will be x of minus t value is minus of x of t. So, all that we are saying is these values are negative with respect to one another, and these two are essentially same in magnitude. Okay. So, the form of Fourier series that we have written actually incorporates both even symmetry as well as odd symmetry, but and then this a0 by 2, which is a constant with respect to time. This a0 by 2 is called as the average value of the signal, okay, and this a0 by 2 is given by 1 by t integral from say 0 to t xp of t dt. This is an integral, which means you simply find out the area of the periodic signal over one period. I have written this from 0 to t, but any time period which is of 1 t duration is equally valid. So, you could integrate from minus t by 2 to plus t by 2 and essentially obtain the same thing over there, and then this is the DC or the average value, okay, and we write that average value as a0 by 2. Sometimes it is also written as just a0, it depends on what you want to write out there, okay. And you can find out what this an and bn are. So, an will be 2 by t integral say minus t by 2 to plus t by 2, the periodic signal multiplied by since we have already written this one, that would be cos n omega 0 t dt. Okay. I will tell you the physical interpretation of this. What this actually means is that suppose I have a device called as a mixer or a multiplier. Okay. You can find this in electrical engineering, you actually can build mixers, and we use this concept very much. So, you have the incoming signal, which is periodic signal xp of t, and then you multiply this one or you mix that xp of t with a signal which you generate from say some function generator, which generates a signal of frequency n omega naught of whatever the amplitude that you want to set. So, you may want to take this 2 by t to the amplitude of the function generator and then do it, right. So, you have say 2 by t cos n omega 0 t. So, this is something that you have generated, and this is something that is incoming, okay. And then you look at the integration, and you will learn later on that this integration is essentially performing what is called as low pass filtering, okay. The integration performs an operation which we call as low pass filtering, okay. And whatever the output that you get will be an, and of course, this is just one particular value that I have found out. You can extend this idea for n equals 1 to infinity. Conceptually, you can extend this idea for n equal to 1 to infinity, okay. This operation of xp of t multiplied to cos n omega 0 t, which is realized by this operator or this particular device, which is called as a mixer or a multiplier, and then taken it to the low pass filtering, which is this integration operator, is an extremely important aspect, because in practice by some modification to this fundamental picture is how you analyze the spectrum of the signal using what are called as spectrum analyzers, okay. There is a device called spectrum analyzer, which you can see, which will actually take the incoming signal and then display for you the different spectral quantities that are present, okay. And this is the basic idea of a spectrum analysis. You will have a bank of such filters, and then each filter will be multiplied, or you have bank of generators, each generator output will be multiplied by the incoming signal and then low pass filtered to generate the appropriate an and bn, okay. The way we have written here is that this is the original signal, or this is the periodic signal, and we are analyzing the signal in terms of its harmonics, okay, an and bn. For bn you can replace cos by sine and the formula would essentially be the same. So, replacing cosine by sine will give you the values of bn, okay. Now, the physical significance of this an bn is that there are many ways to interpret that one, but one important aspect is to look at the power content, okay, which allows us to nicely introduce you to two aspects that will be important when we deal with signals. One is the energy of the signal and the other is the power of the signal, okay. Energy of the signal, which let me express this as exp, or in general I will write this as ex, okay, is given by this integral, In general, you know that signals are going to have range from minus infinity to plus infinity, and then x square of t, x is a real signal. There are situations where you can use complex signals, but I am not going to talk about that one here. This is a real signal. So, what you do is you take x of t, in general a signal, and then square the signal, the value of the amplitude at every time t, and then look at the area under that squared signal. Okay. So, that will give you the energy of a signal. Okay. At the same time, we can also define an average power as this quantity in which we take a signal over one duration or one time duration t seconds, x square of t dt. Okay. So, because power and energy are related by energy to time, energy expended at a rate t will give you the power, that would be called as the power or average power of the signal x. Now, when you look at a periodic signal and then square the periodic signal at every instant t and generate xp square of t, so what would you actually try to get, what would you get when you take the periodic signal, square up the values at every time t and then integrate it, that is you sum or you take the area under that one, you will clearly see that this exp would essentially be infinite, right, because the signal extends all the way from minus infinity to plus infinity, everywhere you are squaring and then looking at the area under that, in general it would be infinity. Okay. So, periodic signals are characterized by having an infinite energy. Of course, no physical signal would be infinity, ranging all the way from minus infinity to plus infinity, but ideally in the ideal sense, periodic signals will have an infinite energy. But if you evaluate the same thing for the power, in which you just take over one time period and square up the value, unless the function itself has infinities in that particular fundamental period, you will see that the second integral, which is p x p, would always be finite. Okay. So, in that case we call as a signal which has a finite power, finite average power and an infinite energy. Okay. So, all periodic signals, mathematically speaking, in general have an infinite energy and in general have a finite power. Okay. So, that is something that you need to look at. Now, the power that you have written here for a periodic signal can actually be obtained by the knowledge of A0 by 2, An and Bn. Okay. To do that, let us rewrite this Fourier series in a slightly different manner. Okay. By making use of some trigonometric identities, you can write the periodic signal xp of t as C0 plus sum n equals 1 to infinity Cn cos n omega 0 t plus theta n, where Cn will be given by square root of an square plus bn square, okay, and then you have theta n being given from minus tan inverse of bn by an. So, theta n is called as the phase angle and Cn is the amplitude of that particular signal. Okay. So, you can write xp of t in terms of only cosine n omega 0 t, but with the amplitudes written as Cn. Okay. And you can then show, unfortunately I do not have time to show this one, that each component that you are looking at C0 square, Cn square, or rather C0 square plus, and by the way C0 is actually equal to A0 by 2. You can show that the average power in this periodic signal is actually given by this expression, that is you take the Cn square by 2. So, you can show that this is something that you can show later on, that the average power in the periodic signal is given by C0 square plus the summation that goes from n equals 1 to 2 Cn n equals 1 to infinity, I am sorry, there are an infinite number of Cn terms, Cn square by 2. Okay. This idea of power and the Fourier components of that one, or the Fourier components or the Fourier series coefficients is very important. This is for the this is for the continuous time aperiodic signal. You will see a similar relationship for the continuous time aperiodic signals as well. This is for the periodic signal, and a similar relationship will be there for the aperiodic signal as well. Okay. Now, in general, you can actually plot these Cn's and C0s. So you have n equal to 0, so for which the amplitude is C0, and then you have n equal to 1, you have the amplitude of C1, n equals 2, you have the amplitude of C2. And this picture, if you plot it in this way, the magnitudes of these, okay, if you plot this way, then this is called as amplitude or magnitude spectrum. And lines, because you have values defined only for n equal to 0, 1, 2, 3 and so on, the corresponding values of C0, C1, C2, C3 and so on, this is called as a line spectrum. Okay. So, this is called as a line spectrum. Okay. You can also plot theta n values as a function of n. So, you will have some theta 0, you will have some theta 1. I am just plotting some arbitrary values. Okay. So, clearly I am not really plotting them by for a given signal or something. I am just plotting these arbitrary lines out there, and what you can then call, or what you then call this picture, the one that is in the bottom, as the phase spectrum. Okay. So, when you plot Cn's and then when you plot the corresponding phase, you call this as the amplitude line spectrum and the phase line spectrum. And to obtain what is called as a power spectrum, okay, which will again be a line, all you have to do is to square this up, divide each component by 2. Is that okay? I am not sure how many of you have heard this, but there was an instrument called as Harmonic Analyzer, and the Harmonic Analyzer was exactly doing this one. It would, analyze the signal by our conceptual block diagram and then plot C0 square by 2, C1 square by 2, C2 square by 2, and then generate the amplitude or generate the power line spectrum or the power spectrum. Okay. And today's modern spectrum analyzers essentially do the same thing. They will allow you to visualize what are the different frequency components that are present in xp of t. To give you an example which would clarify these ideas, let me just give you the expressions, because I do not have time to derive any of this, but you can do it at your leisure. Suppose I have a signal that is periodic, which is a pulse train, which can again be generated by function generator. So, let us assume that this is some minus t by 4 to plus t by 4, this is t by 2. So, this is the fundamental period that I have, some amplitude a, does not matter what that amplitude a is. So, if you look at this function as it is, you will see that there are essentially, you will see a set of square pulses, right. So, there is some spacing between the pulses, this is a 50% duty cycle, you see these pulses. Now, if I were to ask you what are the different frequencies that are contained in this signal, you will not be able to say, or you will not be able to find out just by looking at it. But if you can, or if someone else can derive and give you the values of Cn, C0 and so on, and if you plot that one, then what you are essentially looking at is the spectrum. Okay. And what that plot tells you is that I have to take a constant of C0, to that I have to add a contribution of a cosine wave. Okay. So, contribution of a cosine wave C1 with an amplitude of C1 cos of omega 0 t plus some phase theta 1 plus C2 cos omega 0 2 omega 0 t plus theta 2 and so on. Okay. That is what that picture is telling you. That is, this is essentially the analysis equation that I am writing, right. What this means is that, conceptually what this means is that you have some constant C0 with respect to time. Clearly, this is not function of time. So, there is a C0 out there, and then you have to take a cosine wave, and then which cosine wave? The cosine wave should have a specific amplitude of C1 and a specific amplitude of theta 1. Okay. And then you take that cosine wave and add that cosine wave at all points to the constant C0. This is an amplitude C1. Then you will also have to take another cosine wave with a frequency which is 2 omega 0, okay, which means that its frequency is higher. So, let us say that amplitude is C2 here. I am probably not writing it correctly, but this should actually be twice the frequency of the white one, and the amplitude of this one is C2, and maybe the phase also, right. So, you have to also ensure that the phase is different. So, this phase is about theta 2. Okay. So, what we are saying is that the periodic signal can be thought of as the superposition of the average or the DC part, as we would call it. This is average value or the DC value, plus a cosine wave of frequency omega 0 with a phase theta 1 and with an amplitude C1, and a cosine wave of amplitude C2 phase theta 2 and with a frequency of 2 omega 0 and so on. Okay. And when you add all these sinusoidal signals plus the appropriate C0 with appropriate phase and amplitude constants, you will actually be able to generate a signal which would actually be this original signal, right. So, although this is a time domain signal, this time domain signal has been synthesized by many additions or superpositions of the cosine waves. Okay. This is the synthesized, and when you synthesize them, you will essentially synthesize a square pulse train. Okay. So, this is what the meaning of this one is, right. Okay. Yeah. Yeah, I will come to that. You can take this as an exercise or something. I do not have time to derive it, but what this is the power in the function, or this is the power in the signal xp of t. Okay. And the average power, as we have already defined that one, is given by whatever the integration over one time period of the function xp of t or xp square of t, right. So, if you go back to this periodic signal, this is the amplitude A. To write down what is xp square of t, you will have to square this one. So, when you square it, the amplitude becomes from A to A square, and then you are integrating that one over this time period, okay, and then dividing that integrated value by 1 by t or dividing it by t. So, what we mean there is that we are taking the area under this and then dividing that area by capital T to evaluate what is the average power in this signal, Now, instead of doing this one in the time domain, you can do the same thing in the frequency domain, provided you know C0, you know C1, you know C2, you know C3 and so on. Okay. In fact, this square wave can be written as some C0, which I do not remember, plus 4 by pi cos omega 0 t, something like minus 1 by 3 cos 3 omega 0 t plus 1 by 5 cos 5 omega 0 t and so on and so forth. Okay. So, this is something that you can actually derive, right. What we mean here is that this signal has a non-zero average value, which is very clear, because for a signal to have an average value equal to 0, then the integration should essentially go to 0, which means it should have both positive and negative parts which are equal, which should cancel with respect to each other. Because that is not happening for this signal, there is a non-zero average value, and then if you apply our Fourier series formulas for A n, B n and so on, you will also realize that you do not need cos 2 omega 0 t in this case. You have to synthesize this pulse waveform by adding up the signals or adding up the cosine waveforms cos omega 0 t, cos 3 omega 0 t, cos 5 omega 0 t and so on. So, all the odd harmonics are present, no even harmonics are present for this particular signal. Okay. And this is the way to obtain the power, right, the average power. But I want to obtain the average power in terms of the frequency domain or the Fourier coefficients, and to do so I have to basically look at this, right. What is Cn? Cn is the amplitude of the cosine wave of the frequency n omega 0, right. Cn square by 2 will be the average power contained in that cosine wave at a frequency n omega 0 t, right. So, I can just plot for different values of n the corresponding values of C0 square by 2, C1 square by 2, C2 square by 2 and so on. For example, for that particular periodic signal, the square periodic signal, you will have C2 equal to 0, C3 will be how much, 4 square by 3 square pi square, C1 square divided by 2 out there, and this fellow will be C1 square, which is 4 square by pi square and so on, right. You can clearly see that for that case these values decrease rapidly, and maybe after 7 or 8, that is n equal to 7 or 8, n equal to 7 or 9 for this signal, the values that you get C7 square by 2 and C9 square by 2 will be so small that they do not really matter. Okay. Now, to obtain the average power, what you can do is to sum up all these values. Okay. Now, why is this important? Because when you filter a signal, you are going to do some operation in the frequency domain. So, let us say you have a filter in this manner, and what this filter does in the frequency domain picture would be to cut off at some frequency, which means only these values or these harmonics or these periods of the cosine waves, they will survive, the rest of them will be thrown out. Okay. So, this is the way filters operate, or you can understand the filter operation in the frequency domain, right. In the frequency domain, it corresponds to eliminating some spectral components. These are all called as the spectral components or the harmonics. Okay. So, this relationship is essentially telling you a relationship in the time domain quantity and the corresponding frequency domain quantity. So, that is what this particular equation means. Yeah. Yes. Well, this is in the time domain. Yes, where are my, anyway, this is in the time domain, which is perfectly fine, right. But a picture that we will write when you write down in this form of a line spectrum is to treat each of these components. So, 0, this 1 is actually f0 and 2 is 2f0 and 3f0 and so on. So, you think of these these values that I have written 0, 1, 2, 3 and so on as the corresponding frequency or corresponding cosine waves of different frequencies f0, 2f0 and 3f0 and so on. Okay. And the corresponding values is what we call as the values at that particular line spectrum.
But there is still time.
Yeah, there is still time, because that is the time. So, if you just wait for some time, I will tell you the actual frequency domain picture. Okay. So, this is, you can think of this as a frequency spectrum, but when you go to an aperiodic signal, you will really see how the term frequency domain comes out correctly. Okay.
Sir,
yeah.
So, you said that usually after C7 or C8 the values decrease or
For this wave.
So,
yeah.
is this usually seen that when n increases the Cn value?
Usually it decreases for any physically realizable function. So, if you have any physically realizable signal, then the amplitudes usually decay as the higher frequency terms go out there.
And so, the other way around usually does not happen. The C0, C1 is small and Cn equal.
It happens, but in a very special type of a signal, which many times is not realizable. Right. You can also have, there are some operations which can actually redistribute the energy. Okay. So, a simple thing like frequency modulation can actually redistribute the line spectrum in such a way that C0, C1 can be lower and C2, C3 can be higher, but those are nonlinear operations which I am not covering here.
So, sir, in most of the cases,
usually it decreases.
frequencies are lower energy.
Yeah, usually for a physically realizable one, higher frequencies have a lower energy. Okay. All right. So, to better appreciate this frequency domain picture, we will look at the case of aperiodic signals. Okay. Aperiodic signals are characterized by having their energies being finite, whereas their power will be 0. Okay. What we mean by this is that an aperiodic signal will, say for example, goes something like this. I do not know the exact way this function would behave or the waveform would behave, but x of t, if you look at this x of t and then calculate the energy of this one, then this energy will actually be finite, because you are taking over the entire range from minus infinity to plus infinity, and then looking at that one, the energy will be finite. But because you are going to divide this finite value by the value of t, which is actually infinite, the power will actually be equal to 0. So, in an ideal case, aperiodic signals will have a finite energy and a 0 average power, okay, which is perfectly fine. Now, how do we analyze such signals using the Fourier techniques, right? We have used Fourier techniques to analyze the periodic signal. We found that the periodic signal can be decomposed into cosine waves of fundamental first harmonic, second harmonic and so on with appropriate amplitude and phase. A similar idea would exist, but now you will not have a line spectrum, you will have a continuous spectrum, because the correct tool for this is called as the Fourier transform. Okay. And the Fourier transform x of f is defined as x of t e power minus j 2 pi f t dt integrated over minus infinity to plus infinity, because usually the range of x of t is from minus infinity to plus infinity. Okay. So, this is called as the Fourier transform. This is called as continuous time Fourier transform, to distinguish this fellow from a discrete time Fourier transform that would also come up later. Okay. I will not spend much time on the Fourier transforms here, although this is very important because I want to go to the discrete time case as soon as possible. But some of the points to note here is that if x of t, so what this again means physically, right. So, let us first look at that one. Physically this simply means the same thing as earlier. I had x of t, I am going to multiply this one by e power minus j 2 pi f t and then integrate it over the entire range. But here I can't really use the low pass filtering idea, because these signals are going all the way from minus infinity to plus infinity, right. In the previous case for a n b n, we interpreted this integration as a low pass filtering operation. Here I can't really do the low pass filtering operation. In fact, what I can do is I can define this entire thing, well, I will put an integration anyway. I can define this entire thing as the correlation or the projection of x of t with e power minus j 2 pi f t. Okay. I will define this as a correlation. Not, this is not strictly speaking correlation, but for our purposes what we mean to say here is that if I have these frequencies e power minus j 2 pi f t, as f varies from minus infinity to plus infinity, I am going to multiply this x of t and integrate it out. I am basically kind of performing what is called as a projection operation. I am projecting x of t onto this e power minus j 2 pi f t, and there are an infinite number of such e power minus j 2 pi f t's now, right, because I have f going from minus infinity to plus infinity. And the result of this operation is x of f. To connect this to the periodic case, I will state without any further discussion, I can actually look at the periodic signal and write the periodic signal as or we will write this as x of n e power minus j 2 pi n by t times t. Okay. I can write a periodic signal in addition to that Cn form that we have written there. I can write it in this form, which is called as the complex form of writing it, wherein we are going to use the complex exponentials e power minus j 2 pi by t times n t, which essentially correspond to e power plus or minus j n omega 0 t. And you know that a cosine wave can be generated by e power plus j n omega 0 t and e power minus j n omega t 0 t, and then add them up, divide by 2, right, and then you can also generate a sine waveform from that. So, this is a same kind of an expression as that, but this is the complex expression. Now, you can at least see the relationship between these two, right. What you see here is the Fourier series. So, you can actually write x of t in terms of x of f as well. So, that would be x of f e power j 2 pi f t df integral from minus infinity to plus infinity. Now, you can see the relationship between Fourier series and Fourier transform. So, what you have here is x of t, which is obtained as x of f e power j 2 pi f t df, but this integration can be thought of as a summation. Okay. If you can write this as x of f n e power j 2 pi f n t df. Okay. So, you are taking this coefficients x of f n, which in the periodic case are written as x n, multiplying it by e power j 2 pi f n t, instead of minus you are multiplying it by e power plus j 2 pi f n t, and then summing up the whole thing to generate x of t. Okay. The same thing is what is happening over here. So, there is a relationship between periodic signals Fourier transform, aperiodic signals Fourier series as well. This relationship, unfortunately we do not have time to develop it much further, but you should get a basic idea of what the Fourier transform is, right. The Fourier transform is still doing the same thing as the harmonic analysis, except now the harmonics are spaced almost close to each other, right, because the fundamental period t in some sense is all the way up to infinity, right. So, the harmonic spacing omega n to omega n plus 1, that has actually been reduced by quite a bit now, right. So, this is the physical interpretation of Fourier transform. Yeah. Because the integration range is from minus infinity to plus infinity. So, over a range of minus t by 2 to plus t by 2 has a certain low pass filtering. Minus infinity to plus infinity is not really a low pass filter, right. Yeah.
The low pass filter idea is
Not really. The low pass filtering idea is related to that integration from minus t by 2 to plus t by 2. That is a conceptual picture, but in practice it is what actually happens. In a spectrum analyzer, you will have a bank, you will have a frequency synthesizer, you will have an incoming signal, you multiply the incoming signal with the function that is generated in the internally in the spectrum analyzer, multiply it, then take the output onto a filter, filter the content and then display it. That is exactly what a spectrum analyzer will do. Okay. Sorry? High pass, I think the filters are discussed later on, right. So, high pass filter will have a different frequency characteristic. A low pass filter is usually something that looks like this, whereas a high pass filter is something that would look like this. Okay. If you look at only one sided frequency response, this is a low pass filter, this is a high pass filter, this is a band pass filter, this is a band reject filter or a notch filter. Okay. Let me point out one interesting part here. See, we have written xp of t to denote a periodic signal which will usually go from minus infinity to plus infinity, but in practice you never have a function which is all the way from minus infinity to plus infinity, right. You will almost have this xp of t over a certain range, say minus L to plus L, okay, where L can be considered to be many periods away. So, L is much larger than t, but L is still finite. Okay. Such a signal can actually be written or called as a truncated periodic signal, and we can write that as xl of t with a superscript, no, let us write a subscript, xl of t defined as xp of t for minus L to less than L and 0 otherwise. Okay. This is called as a truncated periodic signal. So, L is much larger than t, but it is still finite. So, that you have a periodic signal, but it is finite over a certain range, right. Now, there is something called as a rectangular pulse, okay, which is defined as a rectangular pulse of duration L. So, in this case we will make it 2L, okay, is defined as a pulse which extends from minus L to plus L. So, this is t and this amplitude is 1. So, this truncation is the same as taking the original signal xp of t and then multiplying. So, for example, you can think of a periodic signal which is this one, and then you take this xp of t, multiply it with this rectangular pulse of duration L 2L seconds, okay. Then this signal can be thought of as the product of the rectangular pulse and xp of t, right. So, I can concisely write this one in terms of xp of t times rectangular pulse of t by 2L, okay, because the rectangular pulse is actually 0 for t values which are anything above the range from minus, above the range of L and below minus L, okay. The physical significance of this is that if you take the Fourier transform of this, okay, and for simplicity let me assume that this is not any periodic signal, but rather a cosine waveform of some frequency omega 0 t, okay. If I now consider, so what this is modeling is a function generator that has been turned on at some time and turned off at some time, correct. What would be the spectrum of such a signal? The spectrum of such a signal, you can show that one, I will not show it, but I will discuss the importance of that. You can actually show that the spectrum would look something like this. Sorry, these two should have the same amplitude, I just probably did not write the same amplitude, and the spectrum will be centered at omega 0 and minus omega 0. If you plot in terms of the omega axis or omega variable, if you plot in terms of f, this would be f0 and minus f0, okay. You can do this by applying a certain property to the Fourier transform, but what is interesting is that you can look at this. This is not, so there is, so in an ideal scenario, if you take just cos omega 0 t, which would extend all the way from minus infinity to plus infinity, and then you plot the line spectrum for this, the line spectrum will have only one component, or in the complex form will have only two components, one at f0 and the other at minus f0, correct, because only these two frequency terms are going to be present in a cos omega 0 t, because cos omega 0 t can be written as e power j omega 0 t plus e power minus j omega 0 t by 2. So, you have x corresponding to that, and then there is a minus omega 0 term that corresponds to that one, right, with the amplitudes say maybe half and half for that cos omega 0 t. But if you now look at this signal, which is a truncated version or a more realistic periodic signal, then you will see that the spectrum is not just two components, it is still peaking at omega 0 and minus omega 0 or f0 at minus f0, but this pulse has been smeared out, or the peak has been smeared out, and you will also see lot of these side bands. The side bands technically will not go to 0 unless frequency axis goes to infinity, but as I have told you, the energy here or the pulse amplitudes are so small that we do not really need to worry about it, and especially this is true when omega 0 is much larger than this particular width of the spectrum. Okay. What this is telling you is that this may be the ideal periodic signal, but when you look at output of a function generator, a practical version of it, you will see not the two lines, but you will see a smearing out of the spectrum. Okay. And this smearing out can be reduced provided L is made to increase. So, as L tends to minus infinity to plus infinity, or L tends to infinity, so that the signal approaches the original periodic signal, then these pulses or these signals will approach the Fourier series, or the amplitudes would essentially be in such a way that the lobe decreases, the peak increases, such that this fellow will approach this one. That okay? Any question? By the way, this model is very important in many measurements. This is what is going to happen. You will have a finite range of signal to deal with, and the spectrum will definitely smear because of that, and you have to take that into account, and in fact this will tell you what is the resolution of the signal that you can expect. Okay. Anyway, so this is the frequency domain analysis of continuous time signals, and what we now want to do is to look at discrete time signals and then understand how to generate the discrete time signals and how to extend these tools of Fourier Transform and Fourier Series for discrete time cases as well. We will study what is called as discrete Fourier Transform, which is very important in practice, and how to use discrete Fourier Transform and what are the properties of that. Okay. Before we do that, the process of generating a discrete time signal is usually, but not always, done by what is called as sampling the continuous time signal with a sampler or with a function. Let us not introduce this one. With a let us not introduce the function, but just let me tell you what this is. So, x of signal which is continuous time, possibly time limited or possibly bandwidth limited, we will talk about it a little bit. This x of t, instead of looking at the value of x of t at all points, we select specific points, okay, which are denoted by t equals nts, and then generate a sequence which is called as a discrete time signal. Okay. In practice, you will have to also quantize this one, because the values that you generate x of nts could be anything from minus infinity to plus infinity, but you cannot represent those values in any computer or in any physical device. So, you will also have to quantize this. The amplitudes can take on only certain values within a given range and with only those values, but I will skip that part because that will be talked about it later. So, for our purposes, this is a sampler, and sampling operation means you have an original x of t this way, and then you select different points. Okay. You select different points which are usually equally spaced. So, Ts, 2Ts, so maybe you start at x, at some initial point which you refer to as 0, and then you go to Ts, 2Ts, 3Ts and so on. Note down the values of x of t at these values, and then construct either a table or a signal, okay, a tabular value or a signal, and this is called as a discrete time signal, okay, or sometimes called as digital signal. There is a small difference between the two which we will not have to worry about it. So, you have gone from continuous time signal to the discrete time signal. Now, when you do that, you have lots of questions. Can I always do this and not lose any information which is present in the original x of t? That is the first question, right? Because if you are going to lose information, then there is no point in doing a sampling, or you may sample, but you are not going to gain anything out there, right? The second question is that how should I choose this Ts, which in fact is related to the first question itself. How do I choose this Ts such that I may actually recover all the information, I may not lose all the information, right? So, that is the first question. I thought there was another question, I will come to that other question, I forget. Okay. To answer that question, you have to look at the Fourier transform of x of t. Okay. Assuming that you know the Fourier transform, then what does the sampling operation do? So, let us suppose some x of t is there whose Fourier transform looks like this, okay, with a finite bandwidth, as we would call it, because the value of x of f for any value of f greater than b or any value of f less than minus b is equal to 0. Assume that I have an x of t whose bandwidth is finite, it goes from minus b to plus b, and any value outside is actually equal to 0. What the sampling will do here, by the way, this Ts is called as the sampling interval. Okay. It will tell you what is the intervals at which you are actually sampling the original continuous time signal, and the rate at which you sample, which is given by 1 by Ts and usually defined as Fs, is called as the sampling rate. So, you may specify 16 Mbps, 16 mega samples per second. That would correspond to taking an original continuous time signal x of t and sampling it at a rate of 16 into 10 to the power 6 samples in 1 second, right. So, that is what the sampling rate would mean. Okay. Now, this is very important. The original signal x of t is assumed to be band limited to minus b to plus b. If the original signal is not band limited, you make it band limited. Okay. You can always do that by appropriate filtering techniques. You can always make the signal band limited, and band limited signal, let us say, is minus b to plus b. Okay. It goes that way. The operation of sampling in the time domain corresponds to shifting in the frequency domain. Okay. And how much you are going to shift will depend on what is the sampling rate. So, if x s of f stands for the Fourier transform of the sampled signal, do not worry how you get that one, that is a different question altogether. But if you look at the spectrum in terms of the Fourier transform of this discrete time signal, okay, which is not usually done, but for our purpose we will do it, this would actually be obtained by shifting the original Fourier transform by those corresponding values. Okay. There is also some amplitude scaling, we do not want to worry about that amplitude scaling, and what you would have essentially seen is that sampling in the time domain corresponds to periodicity in the frequency domain, because this equation is periodic equation or an equation of a periodic function, except that this function is now in the frequency domain rather than in the time domain, right. So, if you actually look at what is happening to xs of f, xs of f would look like this. Oh, sorry, hold on. Now, that is what the point is. Now, I want to relate b and fs. Okay. Let me ask you this, maybe some of you can get this. This is x of f. I know that xs of f will be shifted replica of this one, right. I have to shift all the way from minus infinity to plus infinity, right. What is the minimum value of fs that I need such that the shifted versions do not overlap with respect to each other? Suppose fs is equal to b, okay. Suppose fs is equal to b, then what would we mean? What we mean, I mean, how do we obtain this xs of f? This would be x of f minus nb. Period from minus b to plus b by a value of b, right. So, I am going to get a spectrum that would look like this. In this case, you can clearly see that the sampled spectrum is actually getting distorted, because you are going to see that this would actually be something like this. So, I mean, you will have to add up all these terms, and when you add them, they will essentially become a constant. That is not a really good spectrum, because the original spectrum which was present here has now been invaded by the spectrum from the lower side as well as the spectrum from the higher side. Okay. And this phenomenon in which the original bandwidth is actually getting distorted is called as aliasing. I will tell you what aliasing in a moment, but this is a general principle, right. You do not want that to happen. You do not want the spectrum to be aliased, because when it happens, then your original spectrum is distorted and you have lost information. Okay. So, taking Fs is equal to B is no good. What would be the minimum value that I can take? Clearly, if I am going to shift this spectrum, which was at this component which is at minus B, to a value such that it should not overlap, I have to choose this point at least such that it goes to plus B, right? It just touches B, because when that happens, then the spectrum that you are going to get will be barely touching each other, right? So, minus B plus Fs should be greater than or equal to B is the condition that you need to satisfy in order that these spectral regions do not overlap with respect to each other. This implies that the sampling rate Fs should be greater than or equal to 2B. Okay. If a signal has a bandwidth B, although a signal has a bandwidth B is represented by a spectrum or the Fourier transform from minus B to plus B, the bandwidth is still B, and the sampling rate, minimum sampling rate that is necessary will be greater than or equal to 2B. If you sample at any other value, you will actually be able, you will be distorting the signal and you will not be able to recover the original signal correctly. Okay. That is the first point. The second point is that sometimes, and this is the reason why you need to use filters to band limit. Suppose I have minus B to plus B, this is the signal spectrum. Let us also say that there is some noise spectrum here, okay, which is away at that particular point, right. So, this is noise, this is your signal, this is the frequency f. Suppose I choose my Fs to be greater than 2B, right. When I do that one, if I concentrate only on the signal part, I am going to see that. So, let us say I have chosen it in such a way that Fs is greater than 2B. So, I am going to have the spectrum that would look like this and then go all the way out there. But in addition to signal, the noise is also getting shifted, because noise is also being sampled. You can't distinguish when you take a signal which also has noise in it, you can only isolate the signal and then sample it, right. You are sampling both. So, noise spectrum, the effect of that in the frequency domain is that the noise spectrum also shifts, and this fellow will shift and usually will fall right into this one and then add noise into the, could have been, if you had used a continuous time Fourier transform, you could have distinguished signal and noise. The sampled signal will have a Fourier transform in which in the band of interest you have noise spectrum also. So, this means that you cannot distinguish signal and noise in this bandwidth, and therefore, what you have done is sampling or converting an original signal which is still noisy, but the original signal that has after being converted, you cannot recover the signal correctly, right. In the original case, you could have with some approaches, because signal and noise were separate, but after sampling, after converting the original signal into a discrete time signal, your noise is now within the band of interest, and this is one of the major problems with discrete time processing, that noise can actually seep into the bandwidth of interest. In order to avoid that, you have to limit the bandwidth of the signal which you are sampling to whatever the range that you want to do it, okay, by what is called as anti-aliasing filters. Incidentally, Fs equals 2B is called Nyquist rate, and Fs by 2 is called as fold over frequency, or sometimes called as Nyquist frequency. Okay. Fs by 2 is called as fold over frequency or Nyquist frequency, and because everything is periodic with a period Fs, the sampled signal, the bandwidth of interest will be always from minus Fs by 2 to plus Fs by 2. Okay. Any question? All right. I will give you an example. Let us assume that I have an original signal x of t, which is continuous time signal, which is sin 2 pi 1000 t. Okay. This is a pure sinusoidal signal, no noise, nothing whatsoever. I have this signal x of t. This is a periodic signal, but we do not really need to worry about that. Okay. I convert this signal into a discrete time signal. Okay. How do I convert? I have to sample this one at t equal to nts, and let me take Fs to be about 4000 samples per second, Am I doing okay with respect to Fs? Yes, because the bandwidth of this one is about 1000, 2 times 1000 is 2000. I am in fact oversampling it. I am oversampling it by a factor of 2, which is all right, right. So, what would be the corresponding discrete time sequence or discrete time signal? That would be x of nts, where n again goes from whatever minus infinity to plus infinity. But look at the expression. I have sine 2 pi 1000, Fs is 4000, Ts will be 1 by Fs, correct. So, 1000 by 4000 n, correct. This is the discrete time sequence or signal. Obviously, this will cancel with respect to each other, 2 and 4 will go away. So, what you get is pi n by 2, and remember n can take on integer values. Let us take n equal to 0, 1, 2, 3, 4 and so on, okay, and then plot the numbers out there as a function of n. Okay. So, when n is equal to 0, what is sine of that? 0, and when n is equal to 1, what will be the value of sine pi n by 2? That would be 1, correct. And when n is equal to say 2, what will happen? That would be sine of pi, that would be 0, and when n is equal to 3, you will have minus 1, correct. This is 1, 2, 3, so this is plus 1, this is minus 1 and so on, right. So, this is the signal. Now, if you are just given these numbers and asked, think about it a little bit, if you are just given these numbers, maybe you want the numbers also on this side, you can generate them, and these numbers are given to you and asked to find out what is the frequency of the original continuous time signal from which we have derived this discrete time signal. Will you be able to tell us? If I do not give you the value of Fs, I just give you these numbers, will you be able to determine what is the original frequency of the signal? You will not be, because let me take another signal which we will call as some x1 of t as the same sine 2 pi, but instead of 1000, let me take this to be say 5000 t, okay, and then sample this one, but sample at the same rate 4000, okay. What do I get? I get sine 2 pi by 4 5 n, which obviously means pi by 2. What would this be? 5 pi by 2 n. 5 pi by 2 is basically sine of 4 pi plus pi divided by 2 times n. Is that correct? So, I can rewrite this as sine of pi n by 2 plus 4 pi by 2. Obviously, 4 pi by 2 is 2 pi, and you know that sine functions are periodic. So, if I write this as 4 by, I mean when I add 2 pi to the original signal, nothing really happens. So, it does not really matter. I got pi n by 2, right. If I generate n equal to 0, 1, 2, 3 for these values, if I generate the samples of x1 signal, that is x1 of nts, right, where will these sample values go? The sample values will go sit right on these ones, right. This phenomena is what is called as aliasing. You can't distinguish from the original 1 kilohertz signal, which was your signal, from a signal which is 5 kilohertz. In fact, you can't distinguish any signal if the original signal is some f0. All the signals which are of the form f0 plus kfs will generate the same samples, and you cannot distinguish these two samples at all. Okay. So, what has happened? The sine 2 pi 5000 t is actually a high frequency signal, but it is actually looking like a low frequency 1 kilohertz signal, right. Similarly, a 10 kilohertz signal would also go back and look like a 1 kilohertz signal, and so on and so forth. Maybe not 10 kilohertz, we will have to figure that out. Any frequency that is there in this f0 plus kfs will be equivalent to f0 itself of the original frequency, okay. And this problem is what is called as aliasing. So, to determine the spectral components or to determine the spectrum of the discrete time signal, it is very important that you know what is the value of Fs. Without knowing the sampling rate, you cannot avoid the aliasing problem. In fact, that is just a dramatic description of the same thing that is happening over here, right. See, look at this excess of f, right. the value of this fellow will be the same at this frequency as well, correct? The value of the spectrum is the same at this frequency as well as at this frequency. In fact, it is the same at this frequency and so on and so forth, right? In fact, and these two will be actually separated by that Fs value, maybe not these two, this and this will be separated by Fs, this and this will be separated by Fs, right. So, the values which are all Fs separated in the original spectrum will always alias into the given band, okay, and that is what you are actually seeing. So, if you look at the original 1000 1 kilohertz spectrum, that was 1 kilohertz spectrum here, and then the sampling rate was for 4 kilohertz. So, a 5 kilohertz signal which was present here would actually translate back into 1 kilohertz band, and for a 4 kilohertz sampling rate, the band of interest is from plus 2 kilohertz to minus 2 kilohertz, and any signal which can be shifted into this band by appropriately translating it by Fs will always fall into the frequency band of interest and contribute to aliasing. Is that okay? So, to avoid aliasing, use anti-aliasing filters to limit the bandwidth and specify the value of Fs clearly. Okay. So, that is the connection between continuous and discrete time signal. There is one very important topic which we will now look at. I hope I have time. Yeah. Yeah. You will still have to do anti-aliasing filter, because you may, unless you know that there are no noise spectra out there, you will still have to do that anti-aliasing because but that is essentially what an anti-aliasing filtering is, right. So, in some way, if you do not limit the bandwidth, then anything which is there can shift back. No, you can avoid. So, see, the problem is that once you have crossed the Nyquist frequency, there is no problem, sampling will work correctly, but then if you are concerned about noise, then you cannot, because assuming that there is noise which is not already been filtered out and the noise exists, then that noise would always alias back down to the frequency band of interest from minus Fs by 2 to plus Fs by 2. So, selecting the right sampling rate will not avoid the noise problem unless you know that there is no noise which can contribute to your signal. So, that will always happen. Yeah, no, if there is no noise and your Fs is greater than 2b, then there is no aliasing. But if there is no noise and Fs is less than 2b, there is aliasing. Yeah. Same question. Huh? Yeah, but you need to know that. See, sometimes you deliberately undersample, okay, because there are some components which are at the high frequency and you want to bring those components back into the low frequency. Then sometimes you deliberately undersample, but in general you do not undersample. Okay. All right. So, now let us look at an important topic, which is what most practical things that we do. Suppose I have a discrete time signal, okay, which is generated either by imaging something or by a process which has been sampled. So, you put a sensor, it is going to sense a certain thing, and then generate a discrete time sample values of that, and you store that on a computer. Okay. Now, you want to understand what are the different frequency components that are present in this discrete time signal, right. This is a very important concept. You need to know what are the different frequency components that are present in the discrete time sequence or discrete time signal. Normally, when you talk of discrete time, you talk of sequence. So, I am just using the word discrete time sequence here. It essentially means the discrete time signal itself. Okay. So, suppose I have a discrete time signal. Please note that now I have dropped this Ts in the notation. I dropped that Ts in the notation because in every operation that we perform on a computer, you should know what was the original value of Ts. If you know that, then there is no problem, right. If you do not know, then you have to keep that notation, but you always know that as a prerequisite of a problem, right. So, this x of n is simply table of numbers or a set of numbers that has been given to you, and n is an integer. Okay. And let us also further assume that the range of n is fixed. Okay. The length of the signal that you have sensed from some measurement or you have sampled from something is fixed, because maybe that number of points is 4000 or 4 million, but that is still a finite fixed value. Okay. We take that maximum value or the number of such points or the number of such values that are stored in the computer or given to you as a discrete time signal is n. Okay. So, and we will also assume that this n has a range of say 0 to n minus 1. I will tell you why this range is important or what to do with when you change the ranges later on. Okay. So, I have a discrete time signal x of n that has been defined in this particular way. The sample record is of length n and the samples themselves are numbered from x of 0, x of 1, x of 2 and so on, or that is the values. The samples themselves are 0, 1, 2, 3 and so those are the times at which we have sampled. Okay. Now, you have this record out there. How do you find out what frequency components are present in this x of n? You obviously have to go to the frequency domain for that, right? And the correct tool for analyzing this signal is what is called as Dtft, discrete time Fourier transform. Okay. And that discrete time Fourier transform is defined, usually it is defined for minus infinity to plus infinity, but since our signal is finite record, I am just defining it over that range. Okay. If you have an infinite number of values, obviously you can define it from minus infinity to plus infinity. Okay. And what you do here is this fellow. Oh, I am sorry. Yeah. Okay. Its omega is just some variable, not to be confused with the continuous time omega. That is just another omega. In fact, in right. Oh, sorry, there is an n here. I forgot. Yeah, go ahead. Yeah, it is possible. What you are doing is you are generating that x of n and then you are multiplying each value with e power minus j omega n. So, technically what you are doing is still Fourier series kind of a thing, right, but this time you are using the, hold on a minute, I should have written down the notation here. So, this is what you are doing, right. So, what you are doing is you have this set of numbers x of n, to each of that number you are multiplying by e power minus j omega n. The catch here is that this omega is a continuous quantity. Okay. The range of this omega is usually from minus pi by t to plus pi by t, where t is the sampling rate that you have chosen. So, minus pi by ts to plus pi by ts, and what you obtain is the discrete time Fourier transform, which is continuous and it is periodic. Okay. In the case of infinite range for n equal to minus infinity to plus infinity, this fellow will be periodic with a period of 2 pi by ts. Okay. But on a computer I do not have a continuous time, a continuous quantity. I can't have omega varying continuously, because on a computer I can't represent any of that, right. So, in that case we sample this Dtft at appropriate samples and generate what is called as discrete Fourier transform. We generate a discrete Fourier transform. Shorthand notation for this is Dft. Okay. This is a very important tool, and the definition of that one is 2 pi by n k n, and in this case obviously the left hand side cannot be a continuous function. The left hand side is now a discrete function, which we will simply write it as x of k. Okay. I will tell you what this equation is. In pure sense, this equation is the samples of the discrete time Fourier transform, where the sampling is taken at 2 pi by n times k. Okay. But in another way of interpreting this one is that, so for example, let us look at what is x of 0. Okay. What would be x of 0, and the range of k is also same as n. So, both k and n go to the same range, k equals 0 to n minus 1, n equals 0 to n minus 1. So, what this has done is to take a finite set of values of x of n and then give you a finite set of values x of k, or a range of values of x of k. Okay. what is the meaning of these different values of k? I will tell you now. And n is of course the length of the sample sequence x of n, right. First look at what is x of 0. To obtain x of 0, in this expression you have to set k equal to 0, right. And then when you set k equal to 0, what are you going to get? You will get n equal to 0 to n minus 1 x of n, right. You are taking each value x of n, adding them and then summing up, right. In fact, this is equal to n times the average value of x of n, right. This is the notation that I have used for the time averaging. Average value of the sequence x of n times n will be this fellow, because averaging would mean 1 by n summation n equals 0 to n minus 1 x of n. So, this is the average x of n, and then this expression x of 0 will be the average times n. So, if you now look at this x of 0, it is actually telling you what is the average value of the discrete time sequence, what is the average DC value of the discrete time sequence. Okay. If you look at what is x of 1, that is very interesting. You look at this, that is n equals 0 to n minus 1 x of n e to the power minus j 2 pi by n times n. Here you have again a projection or a correlation of two signals. One of them is x of n, which we will have. So, if you expand this expression, I am doing it so that we understand this better. So, I have this as x of 0 times e power minus j 0, which is basically 1, plus x of 1 e power minus j 2 pi by n plus x of 2 e power minus j 2 pi by n times 2 and so on. Okay. If you just look at these quantities, 1 e power minus j 2 pi by n e power minus j 2 pi by n times 2, that is actually a discrete time complex sinusoid, which is given by e power minus j 2 pi by n times n. Okay. This is a discrete time complex sinusoid. You can plot this using MATLAB or Octave to actually see how this sequence looks like, but this is essentially a sampled cosine wave which exactly has n such samples over that range, and this has been sampled. Okay. This has been sampled in such a way that there are n such samples. Okay. And to each sampled discrete time sinusoid, you are going to multiply that one by x of 0, x of 1 and so on, and then sum the entire thing, okay, to obtain x of 1. And then you can do the same thing for x of 2, x of 3 and so on. What you can think of are, those are all different complex sinusoids or different sinusoids which have been sampled in such a way that each of them has a sample n, but the frequencies are all different. The fundamental one will have a frequency of say 2 pi by n, the next one will have a frequency of 2 pi by n times 2 and so on. Okay. In general, the kth term will have the frequency which is given by 2 pi by n times k. Okay. That is what the DFT is. Okay. Now, what is the use of this DFT? Let us first connect the different k's to one another, a different one. We said kth term will have, I just erased it, but that will have the frequency of 2 pi by n times k. But remember, these signals are usually derived, x of n is usually derived by sampling the original signal at a sampling rate of Ts, right. So, someone tells you the original sampling rate of the signal and then asks you what are the different frequencies involved, then you can look at each of the kth term and then actually obtain the original analog frequencies. So, the digital frequency corresponding to this k will be 2 pi by n times k, but the analog frequency corresponding to this one will be 2 pi by n k fs. Okay. I will give an example which will make this thing very clear. So, the kth term in the DFT which you are evaluating x of k will actually tell you the amplitude of the frequency component whose digital frequency is 2 pi by n times k, but whose original analog frequency is 2 pi by n times k fs. So, if you were to actually look at the discrete time sequence, take the DFT, then what you are doing is to generate the different amplitudes of the sinusoidal signals that are necessary to synthesize the original signal x of t, from which you have sampled and obtained x of n. Okay. Let me give you an example. Suppose x of n, or suppose x of t is some sine 2 pi 1000 t, okay, and then you use a sampling rate of Fs equals 4000 and then sample these signals. So, you will have x of nts, which anyway we are going to write it as x of n, as given by sine pi by 2 n, correct. And then we obtained, what did we obtain for this one? Let us also take the range of n to say n to be 8, so that I am generating these samples from n equals 0, 1 all the way up to 7, because that is the range. N equal to 8 means I have to generate samples from 0 to n minus 1, right. So, if I just generate 8 samples, what are the samples that I am going to generate? I am going to draw this in the form of a table. N equals 0, 1, 2, 3, 4, 5, 6, 7. What are the corresponding values that I have? N equal to 0 will be 0, 1, 0, minus 1, 0, 1, minus 1 and 0. Right? These are the 8 values that I am going to generate. Okay. I can now apply Dft onto this and then plot the Dft. I can plot x of k magnitude, because x of k in general will turn out to be a complex number. I can plot the magnitude of x of k and also plot the angle of x of k in another, this one, that if you want. Okay. Now, if you were to look at this sequence, it is obvious that x of 0 will be 0, right. There is no DC component for this. Please, you have to evaluate this as an exercise to really appreciate this, but x of 0 will be 0. So, this is 0, this point is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and that is the enough range for us, because k is also going from 0 to 7, right. Okay. What would be x of 1? X of 1 will in fact turn out to be a finite value, some number, which we will write it as x of 1 out there. Okay. Well, not really, I have to find out, hold on a minute. I will do a little bit of a calculation here. Fs is 4000 divided by n is what? N is 8. So, I will actually get 1, 2, so 500 hertz. Okay. All right. Turns out that x of 1 will also be 0, but x of 2 will be non-zero. Okay. X of 3 will still be 0, and then x of 4 will be 0, x of 5 will be 0, but x of 6 will be non-zero and x of n will be 0. You can verify this. Okay. You can verify this, and I will tell you why those two are going to be non-zero and what we actually have to do about that. If you also look at the phase, you will see that this will be 0, this will be 0, this will also be say 0, 0, 0, 0, but for the sixth one the phase will be 180 degrees. Okay. The phase will be 180 degrees. This is actually a main point of Dft, which we are going to look at. Why do you think that the Dft shows up these kind of plots? Remember, this axis that we have written is an axis for k equals 0, 1, 2, 3, 4, 5, 6, 7, but each value of k in turn corresponds to an analog frequency of 2 pi by n kfs, right. Or if you just consider Fs, then it would be corresponding to kfs by n. In terms of kilohertz, it would correspond to kfs by n, right, or in terms of hertz. In this case, Fs is equal to 4000, n is equal to 8. So, each kth term will be a multiple of k times 500 hertz or k times 0.5 kilohertz. Okay. So, k equal to 0 will be 0 kilohertz. So, obviously, this signal has no DC component. The entire sine function is fitting nicely into the time domain, and therefore, the 0 hertz frequency component is 0. This k equal to 1 in fact corresponds to 0.5 kilohertz, right. So, if I write f in terms of kilohertz, this would be 0.5. Clearly, the signal originally is not at 0.5 kilohertz, right. Therefore, that term will also be equal to 0. At 2, k equal to 2 actually corresponds to analog frequency of 1 kilohertz. Obviously, this should be present because that is present originally, right, and there should be a non-zero value for 2. There is no 1.5 kilohertz and then there is no 2 kilohertz component, right. And remember, the range of Fs, or sorry, the range of interest once you sample goes from minus Fs by 2 to plus Fs by 2, right? And Fs by 2, which is 1.5 here, this is 2 kilohertz, we have exhausted it. Now what would be k equal to 5? In fact, k equal to 5 corresponds to minus 0.5, right? And then k equal to 6 corresponds to minus 1 kilohertz, which is okay because you need e power plus jk omega 0 t and e power minus jk omega 0 t to reconstruct the cosine waveform or a sine waveform, right? So in fact 5 corresponds to minus 0.5, 6 corresponds to minus 1, 7 corresponds to minus 1.5 kilohertz. In fact, what you have seen is that this range corresponds to 0 to Fs by 2 and this range corresponds to minus Fs by 2 to just one below the 0 thing, right? And if you use MATLAB, there is a specific command called as Fft Shift. Okay, Fft is used to obtain the Dft of the sequence, and when you use this Fft Shift onto the sequence that you have obtained, this is what originally MATLAB will plot. Okay, but if you apply the Fft Shift command, then it shifts the center, instead of at 0 here, it will shift the center to 4 somewhere here. Okay, and then you will see, or rather it will actually plot in this way. What MATLAB Fft Shift corresponds to is, there is no component here, no component, then there is one component here, no component, 0.51, 1.5, 2, and then you have no component and then 1 and then this. So this range is 0 to Fs by 2, whereas this range is from minus Fs by 2, minus one component to 0. So basically you don't include the minus Fs by 2 component exactly, because that would be the same as plus Fs by 2 component, right? So you don't include one of the components. That's the difference between the two. But did you understand this? If you take Dft of a sequence and if you don't know what the original Fs is, then you will simply get those numbers. But to properly know what the spectral components are present in your measurement, you need to know what is Fs. And once you know what is Fs, then you know what is the frequency resolution of your Dft. Okay? In fact, this Fs by n is called as frequency resolution, and it is very important to know what is the resolution of that one, and for that you need to know what is Fs. Okay? Obviously, I can reduce the frequency resolution by increasing the value of n. For the same value of Fs, I can increase the value of n to reduce the resolution, or to basically increase the resolution, but in that case the numbers that will be non-zero will also be shifted appropriately, correct? Whereas in this example the resolution was half a kilohertz, so x of 2 and x of 6 turned out to be non-zero values. If you take n equal to 16, then this will be shifted to 4. So you will now have 4 and something else that would be non-zero, right? This symmetry is also an important point. X of t is usually a real signal, and then for real signals the Dft is in such a way that x of k value is the same as x of n minus k value, except there is a conjugation on top of it. Conjugation means the amplitudes would remain the same, I mean equal, but the phase will be 180-degree opposite. Okay? The phase will be 180-degree opposite. So for this x of 2 and x of 6, the amplitudes are the same, but their phase is inverted, 180 degrees opposite. Okay? And the amplitudes are the same because this is the property of discrete time, discrete Fourier transform. I would like to do one additional thing here. Suppose, this is important, suppose instead of 1 kilohertz, I had 1.25 kilohertz. Okay? I am writing this as 1.25 kilohertz, but obviously you have to write it as 1.25 into 10 to the power 3, which is 1000 into that one. Now let me keep the same sampling rate Fs. Fs is still 4000, right, or 4 kilohertz. What would happen to x of, now without doing anything further, if you sample this x of t, which is at 1.25 kilohertz sinusoidal signal with a sampling rate of 4 kilohertz, what do you think will happen to this spectrum? First, figure out what is the frequency resolution. Does the frequency resolution change? Assuming n is equal to 8 samples is what you want. Does the frequency resolution change? No, right? No, it doesn't change. So which means all of them are at 0.5 kilohertz resolution. Okay, let me draw that. You should do this. Okay, what will happen to k equal to 0? So, this is k equal to 0, this is 1, this is 2, this is 3, this is 4, and as we have figured out, only this much is enough, information is enough, because the other information will be usually symmetric around, correct? But if you want, you can also write 5, 6 and 7, right? This is k value, but what is the corresponding analog frequencies? This is 0 kilohertz, half a kilohertz, 1, 1.5, 2, 2. Or rather whatever the negative frequencies, correct? Okay. Now I have sampled at 1.25 kilohertz, I mean the signal is at 1.25 kilohertz, I have sampled at 4 kilohertz, I have to actually calculate what will happen to x of 0, but that is not what my interest is. My interest is what will happen to the terms at 1, 2, 3, 4, 5, 6, 7 as such, right? Do you think that 1.25 kilohertz would show up on either 1, 2 or 3 or 4, any of those components? You get the point? See, the problem is very simple. You have a 1.25 kilohertz signal which you have sampled with a rate of 4000, which is okay, because 1.25 twice of that is 2.5 and 4000 is much greater than that one, right? Or at least greater than that one. So, you have sampled it correctly, but now how does your DFT show up? Will you have a component at 1? Technically the component at 1 would correspond to half a kilohertz, right? Will you have a component at 2? That would be 1 kilohertz. Where should the component be present? In fact, it should be present somewhere in between, but that in between is not defined. This is a discrete time value, so only k equal to 0, 1, 2, 3, 4, 5, 6, 7 are defined. I do not have a 2.25 term here. Then what will happen to the signal energy? It gets distributed to the two things, right? So, you will actually see some non-zero term here, non-zero term here, and maybe the amplitudes will be slightly different, do not bother about that. And because of symmetry, you will also see terms which are at, so 8 minus 2 is 6, and then 8 minus 3 will be at 5, right. This is called as spectral loss. Okay. To overcome this, there are some techniques that you can do. If you go simply by the idea that I have n, right, I have an expression for x of n, let me increase the value of n. Okay. I have x of n, which is something that I have. Let me now imagine that I do not know what the original sequence are, but I have been given a value of x of n. Okay. I do not know what the original x of n are, I am given the value of x of n. What I can do is, I know that originally this was defined from 0 to n minus 1. I can extend the range from n minus 1 to m. Okay. Then what does it do? And when I extend the range, I will also make this one go to 0. Okay. I will also add zeros. This is what is called as zero padding or appending zeros, right. Now, what will happen to my frequency resolution? My frequency resolution is now become Fs to Fs by m, and m is greater than n, or rather m minus 1, no. So, m is greater than n. My original range is now 0 to n minus 1, I mean 0 to n minus 1 was the original range, now it will be 0 to n minus 1. What do you think will happen to the expression of x of k? X of k, check this, n equals 0 to n minus 1, x of n e to the power minus j 2 pi by m n k. Is that correct? Yes, because the values that you have added n to m minus 1, they are all zeros. So, the summation actually has no effect whatsoever on this, right. So, everything is still 0, but the frequency resolution has increased. How do we understand each of this? While the frequency resolution seems to have increased in this case, but because we have added 0, we have not gotten any new information. To be correct, what we should have had is the access to the original signal x of t and the corresponding samples at these points. Without those correct samples, even if I have increased m and seems to have increased the frequency resolution or reduced the frequency resolution, whatever way you think of, I have not gained new information, right. So what in fact would happen is that the energy will still spill over into multiple bins, as we would call them. These are called as bins, frequency bins, but then you don't really get only 1.25 and minus 1.25. I mean the corresponding values of k, you won't get only those two things. So just by zero padding, you will not always, in fact most of the times you won't have actually obtained the correct DFT, right. Where will this be useful? Suppose you have an original Dtft, okay, which is x e power j omega, and then you want to sample this original Dtft with a nice looking picture, right. In that case, instead of taking n values, you can take m values, pad them with zeros and then sample, okay. Then you will be generating, suppose x of e power j omega originally looks something like this. With n, you would have sampled them here, okay, you would have sampled them here, but with now zero padding and increasing m, you would have sampled at these values in addition to these values. So you seem that the lines kind of have moved closer, but that is okay for this case, but that is not okay for an actual measurement case, right. So this is only going to interpolate the values in between, doesn't really add new information, okay. So when you look at DFT, this is very important that you have some idea of the sampling rate, because without knowing the sampling rate, you don't know how to look at the values of k. On a computer, you don't evaluate x of k, you evaluate what is called as fast Fourier transform, okay. Fast Fourier transform is the same as DFT. Most of them think that they are different, but they are actually same, except that FFT is an algorithm that is used to implement DFT faster. Yeah. Huh.
It's good when you have a signal of larger length.
Yes, but you need to have the original signal of larger length, not just appending zeros. Right. Appending zeros has its different kind of an effect.
Appending zeros will distribute the
Energy also it will simply distribute, but you won't ever get just 1.25 and minus 1.25.
You get 1.23 and
You will get something like that, yeah. But if you had the original signal samples, when you instead of appending zeros, if you append the actual signal values, increase m, then you will get a better, yeah. In that case, you will approach the original 1.25 kilohertz.
so sir, having the appropriate length is important and sampling at the sampling frequency is important. Both of them are important.
Both of them are important. If you undersample, you just have 2 samples or 3 samples to work with, you won't get the required resolution.
The sample will give us wrong frequency information.
Yeah, and then if you have a smaller length, will give you horrible frequency resolution, right. So in fact, FFT based spectrum analyzers actually work like this. So you have to lengthen the record, but then when you set the time interval larger, it will actually sample the original signal correctly, okay. So appending zeros is for different reason. In discrete time signal processing, appending zeros has its own place, but that is in what is called as evaluating convolution, okay. There it is okay, right, but not in this particular case. So physically, you don't gain any new information by adding zeros. I mean, when you have to add zeros, why stop at only m? You can stop and keep adding zeros for all the way, but you don't generate new information, right. So that problem is called a spectral loss, sometimes called a scalloping loss, and or spectral leakage, sometimes it's called. So that's a very important aspect of DFT that you should remember. FFT is the same as DFT, the equations remain the same, and there's also some notion that in FFT n has to be an even number, usually multiple of 2. Not necessary. There are many algorithms in which n can be just a prime number as well, so it will still work the same way. But this is like, you know, LCM, taking LCM of 2 numbers. You can have different algorithms, but the basic process is the same. One of the algorithms could be faster, the other could be slower, okay. So that is the DFT, okay. Now connected to DFT is the Dft power spectrum. So if you take x of k and then take the magnitude square of that, that would tell you the power, right. We are time up, is it? Okay. Sorry, I don't have any this one for signals, but someone else talk about that one later on, okay. If you have any questions up to this part, please feel free to ask. I'll be very happy to answer. Okay, all right, thank you very much. Huh.
What is the frequency at which the frequency of a signal, and I don't know whether there is noise or not. So how should I select the sampling rate and how should I select the aliasing, the filter?
Nothing known, then it becomes very difficult to answer this question. you should have some information about what is the possible frequency content of the signal. Otherwise, it's completely unknown problem. See, if you just have some numbers or a signal, right, it's very difficult to find what would be the sampling rate. There are some techniques of bandwidth estimation that one can perform, okay, by taking the short segments of the signal and then taking the Fourier transform, and then looking at as you change the record length and see where the signal energy falls off. So you can look at this technique, estimate the bandwidth, and then select the aliasing part. Now, to remove the noise from the signal is a very different question, right? That is like what is called a signal recovery. From the signal plus noise, you are trying to recover the signal, and there are a lot of techniques for that, but that's a completely different subject. Just by spectral estimation or just by sampling, you won't be able to recover signal, or you cannot distinguish signal and noise.
And how do I select if I know the frequency?
Huh.
Let's say select the non-aliasing range.
If you know the frequency, then it's always greater than or equal to 2B. Although in practice, at least in oversampling, this one of about 4 times is preferred. So anywhere from 2 to 4 times. That is to say, 2 times 2B or 4 times 2B, where B is the highest frequency content that you can kind of estimate. In fact, there is an entire area called as power spectrum estimation or spectral estimation, whose job is to estimate the bandwidth of the signal. Yeah.
In a simplified form, sir, like
Yeah.
if my required, if it's a beam and my mode, let's say third is 100 and I require up to mode 3,
Okay.
100 hertz.
Huh.
So what should be my sample, what should be my sample frequency and the number of samples?
So if assuming if you have already specified m equal to 100,
Yeah, that's I found through finite element, and around
Yeah.
it would be, let's say, 100.
then anything technically greater than 200 should work.
And number of samples, sir?
Number of samples, again, you have to, so you are asking for the number of samples. 100 hertz is the fundamental frequency for you, right?
No,
I mean, some mode 3 frequency. So 3 times this one. The number of samples decides what is the next objective for you. I mean, if your objective is to look at the spectral content or something, then you choose the number of samples in such a way that on the discrete spectral case, you are at least covering that required range, right? So in any case, if you take Fs equal to say 300, for example, then the Fs by 2 will be whatever that value, and if you take n as a number of samples, then the resolution in terms of Dft will be Fs by n. Fs you have selected to be say 300, so 300 by n. Now, if you just take n equal to 1, then you may not have enough number of samples. If you take n equal to 2, you may not have samples. So you pick the value of n such that when you plot on the Dft scale, you will at least be able to cover those frequencies that you get, right? So up to 100 hertz, right? See, if Fs is equal to, I have to do the math here, but if Fs is equal to 300, the resolution that you are going to get will be 300 by n, right? So your fundamental frequency is about 100, or whatever m equal to 3 is about 100. So what value of n will at least give me 100? N will be of about 3, but that may be too small because you are going to just generate 0 and then 100 and then 1 at minus 100. If this is sufficient and if that is the thing, then that is the bare minimum value of n that you require. But usually you do not want to restrict yourself to only this bare minimum. So you take, instead of 3, you take something that is say 8 or about 16 or so on. So that is usually it is done by taking this as 2 to the power m, where that is a multiple or the power of 2 signal, right. So that depends on what else you are going to do. For example, if you take that samples and pass it through a digital filter, then choosing n equal to anything less than 3 will be a big problem for you. And n greater than 3 will also be a problem, because then you will have to design a digital filter which has a nice cutoff right at this point. So you normally tend to increase the sample size at least, so that the filtering operation, if you are doing a filtering operation, that has a smooth cutoff, pass band and another cutoff.
So with respect to frequency or spectral estimation of the signal, the Nyquist criterion is okay. But if we have to regenerate the signal, like a continuous signal in a discrete form, then
No, discrete to continuous. regeneration is discrete to continuous.
Discrete to continuous.
Huh.
Then 4000 samples per second doesn't seem okay because in a 2/5 in a t period we are only getting 0, 1, -1, 0.
Yeah, in that case you have to increase if you want to reconstruct, but technically you can do with only 2 samples per period. Technically you can do it with only 2 samples per period, but if you want a better interpolation result, you will have to do more samples. But according to the theorem itself, Nyquist theorem, the bare minimum number of samples are 2.
So, but then I know it is a sinusoidal signal.
Yeah, it is a sinusoidal signal, you should know.
So, it is a triangular wave or a square wave then.
Totally, yes, you can't, because the same sampling rate does not apply to a square wave or a triangle wave or a sawtooth wave than it would apply to a sinusoidal signal, because triangular wave will have a usually higher frequency content than the sinusoidal signal. So, then you are undersampled as triangular wave. So, then you are not reconstructing correctly. In fact, there is what is called as a reconstruction formula or an interpolation formula, which places a sync pulse at every sampled value and then reconstructs it.
Nyquist rate is just for spectral analysis of a signal.
No, Nyquist rate is the bare minimum rate at which you have to sample the signal, continuous time signal, so that you can go to the reconstruction correctly. Ideally.
So if this sample is aperiodic,
Huh.
that is also Nyquist criteria.
Well, in the aperiodic case, that is what we have considered. No, x of n was an aperiodic signal. There is no periodicity in that.
Nyquist criteria.
Yeah, it still holds. You have to again go back to the frequency content and then sample it correctly. I mean, x of t, you mean x of t is an aperiodic signal. Then if you have some idea of its bandwidth, then you still have to sample it at the rate which is greater than 2d.
Another question, to go from time domain to the frequency domain, we generally do the Fourier transform.
Right.
Instead of doing that, we can also do the Laplace transform.
You can do Laplace transform. Laplace transform, the problem is it will give you a quantity which is continuous. Yeah, but it's okay. You can still do Laplace transform. In many systems analysis, you use Laplace transform.
Is there any correlation between that?
Yes, for a stable system, that is Laplace transform x of s is exactly equal to the Fourier transform when s is equal to e power j omega. Oh, sorry, s equal to omega, sorry, I am thinking of discrete ones, sorry, j omega, right, because x of s is e power minus st, some f of t or x of t dt, right. So, this is valid, but this is valid only for those which satisfy certain additional conditions, like x of t should be a finite quantity, otherwise it will not be valid.